Alright, hello everybody. We're going to run through a tutorial on conducting and interpreting something called contingency tables. So this statistical analysis deals with associations between two or more variables that are categorical. So you have a categorical response and predictor. Typically, your response variable is a count value. So this analysis evaluates how frequencies for different values of one variable depend on the value of another. So there are two assumptions for contingency tables. The first is that no more than 20% of the cells have an expected frequency that's less than 5. And the second is that no cells have an expected frequency that's less than 1. So when you're running this type of analysis, you're testing the null hypothesis that the frequency of response variable is not contingent on the value of a different variable. In other words, the response variable is not reliant or not influenced by the value of a different variable. Okay, so we're going to start off running this data set here. If you haven't already set your working directory, please do so. Again, you just go to the session tabs, set working directory, choose your directory, and navigate to the appropriate folder. Okay, so real quick background on this study. The study itself evaluated vertebrate dispersed species in fire-prone sclerophyll vegetation. And the purpose of that was to look at mechanisms used by vertebrate dispersed plants for persisting in these such environments. So they looked at the amount of regeneration, whether it was seed or vegetative, and the dispersal mechanisms, whether they were ant dispersed or vertebrate dispersed. Okay, so when we look at the initial data output, notice how it's in this quote-unquote long format with separate columns for each variable. You have your regeneration type, your dispersal type, and then the count. And that's done for each combination of each variable. Now there's something called the xtabs function, and this works very well for simple tables and data. And this, when you run it, it gives you something called a pivot table. So I want you to do that. Okay, so this here is what we call a pivot table, where you see the count for specific combinations, and it's in a much more condensed format. It's easier to read. So for instance, this number here, 25, is the count for plants that had seed regeneration that were ant dispersed, versus 6, which is the count of plants that had seed regeneration but were vertebrate dispersed. So you get how to read it. It's really simple and makes interpretation much easier. So then we're going to look at the summary function, and that will give us the output from a chi-square test. Okay, so draw your attention immediately to this value here. This is the p-value. You have your chi-square value, your degrees of freedom, and then your p-value. So since the p-value is greater than 0.5, it's not significant. Therefore, we fail to reject the null hypothesis. In this case, the null hypothesis is that plant regeneration is not contingent upon dispersal vector. So then we're going to look at the standardized residuals. And we're going to do this by using the chi-square.test function to test the model and its residuals. So you run that, and what this produces is the actual variation of the residuals from what is expected and the movement or the direction of that variation. So for instance, the seed regeneration plants that were vertebrate dispersed, so that's this count, this value here, they are less likely to have regeneration because it's a negative number, and more likely to have seed regeneration if they are ant dispersed. And plants are more likely to have vegetative regeneration. So here we're in this vegetative regeneration area. So plants that are more likely to have vegetative regeneration if they're vertebrate dispersed rather than antidispersed. If they're antidispersed, they're less likely than expected to have vegetative regeneration. So that's how you read and interpret the residuals. So you can also look at the observed and expected. And again, this gives you, so when you produce these tables, again, you're going to use the chi-square test. So to look at the observed value, that you're going to run this model here so you can see the actual observed values, which are the ones that were actually obtained, and compare those to the expected values, which are those that are expected to occur in nature. So here's your observed, here's your expected. The residuals are the differences between your observed and your expected. So you can actually quantify, again, the dispersion between the observed and expected values by using the residuals. Okay. I'm going to move on to something called odds ratio. Now, an odds ratio is the probability of success divided by the probability of failure. In other words, and I'm going to write out the formula for you here. You have your odds ratio, is equal to the probability of success, which is P, divided by the probability of failure. Now, the probability of failure is measured by 1 minus your probability value. So this is the equation for your odds ratio if you wanted to calculate it by hand. For us, it's pretty easy. Now, sorry, before I go on to that, the odds ratio, the purpose of it is to allow us to evaluate the magnitude of an association between two variables. Okay, so for us, like I said, it's pretty easy. So, for example, the odds of being antidispersed versus vertebrate dispersed if you're a seed regenerating plant. So what you could do is you can go back down here to our observed values. So this is the probability of being a seed regenerating plant that's antidispersed. And this is the probability of being a seed regenerating plant that's vertebrate dispersed. So if you want to get the odds of being antidispersed versus vertebrate dispersed, all you have to do is take 25, that count, divided by the count for the seed regenerated plants that are vertebrate dispersed, in this case 6. So you can just run that in R, and this gives you the odds ratio. So the odds ratio of being ant dispersed versus vertebrate dispersed, if you're a seed regenerating plant, is 4.17. And that's, again, your odds. Again, the odds being ant dispersed versus vertebrate dispersed. Okay. So there's another way to also calculate so this is more of the odds, and then you have the odds ratio. And that's a proportion of the diagonal. So the odds of one group divided by the odds of another group. So again, looking at your observed model output, per se, what you would do, in this case, you would take your 25 times 21 divided by 36 times 6. So what you have right here. And again, that gives you the odds of one group divided by the odds of another group. So we're going to run that. Okay, so this gives us an odds ratio of 2.43. Now you can also do this with a Fisher's exact test, and that will compute the confidence interval for you. Now if the confidence interval contains a 1 in the range, or if it falls over 1, you can say, then it's not significant. So we're going to run the Fisher test. Okay, so looking at our p-value, we get something that's greater than 0.05, so not significant, meaning we fail to reject the null hypothesis that the true odds ratio is equal to 1. Now this is substantiated by the confidence interval, which we see here, because the interval itself contains 1. So because it contains 1, there is a possibility that the odds ratio could be equal to 1, and therefore you fail to reject the null hypothesis. Okay, you can also do a g-test. Now, the g-test function is not included in R. So you actually have to source the previously written function that calculates it. And I have the script to do so. So it's this really long function here. So if you wanted to run the g-test, you can run this coding here, and I'll run it just for fun. And you can get this from that website that's here in this website here. It's at the University of South Carolina, I think. Okay, so if we ran the g-test on our model, we get the actual likelihood ratio. So we get the ratio statistic, and then your degrees of freedom, and then the p-value. And again, looking at this output, it coincides with what we came up with before from looking at the Fisher's test. Again, you have a p-value that's greater than 0.05, so you fail to reject the null hypothesis. All right, so there's an interesting way to actually look at the output visually. And you can do this through a mosaic plot. So we're going to run that, and that's the function to run that is just mosaic plot. And then you have your model that you're running, and you have shade equals true. And that's because the actual gradient of deviance in the model between the observed or the expected is given on a shade gradient or a color gradient. So we're going to run that. Okay, so this is the model that we get. Down here we have, so this column represents plants that are have vegetative regeneration, and this column here represents plants that have seed regeneration. Going across horizontally, this box and this box both represent plants that are antidispersed. These two boxes down here represent plants that are vertebrate dispersed. So if you see color, there is a significant difference from what is expected, and the shade of that color indicates the value or severity of the difference, and this is interpreted on this gradient that's given right over here. Here's the legend for it. So the darker the shade of color, the greater the difference. If you see something that's in the reds, so anything with like this dotted outline that goes from either white to red, and again has a dotted outline, is less than what is expected. Conversely, if you have something with a solid black outline and ranges from either white to blue, you have something that is greater than what is expected. So this half, the top half, the observed is greater than what is expected. The bottom half, you have the observed is less than what is expected. So interpreting this, the first thing you want to look at is seeing whether these boxes are in proportion. Now, if they're in proportion, you would have an even cross between them. Here we have something what we would call a zigzag. So because you have that zigzag rather than a cross formation of the spaces between the boxes, you would say that these spaces are not in proportion. And therefore, because they're not in proportion, there is an interaction. So vegetative regeneration, so we're looking in this area here, is more likely to be dispersed by ants rather than vertebrates. And we can interpret this because of the size of the box. The boxes for ants is much larger than that of the vertebrate dispersed. However, the value we actually have for the observed for the ants is less than what is expected. And we interpret this because it has the ant box for vegetative regeneration has a dotted outline and is a white box. So we go over to our legend and we see that it's in this range from 0 to -2. So it's up to 2 times smaller than what is expected. And then seed regenerating plants, so now we're over in this column, is more likely to have ant dispersed rather than vegetative dispersed. And again, we interpret that because of the size of the box. This box for the ants is much larger than that of the vertebrate dispersed. However, when we look at the box, we see that the observed value, so this box correlates to this here on the color gradient. So interpreting that, we see that the observed value is greater than what is expected, up to 2 times greater. Now, if this box had been, this color here, we could have said that the observed value of ants, while plants with vegetative regeneration were more likely to be ant dispersed than vertebrate dispersed. If this box had been red, we would have said, however, the observed value for the actual ant dispersal for plants with the vegetative regeneration was 2 to 4 times smaller than what is actually expected. So that's how you interpret mosaic plots. And they're really interesting, and they let you see kind of a visual representation of those residuals, which is, again, the difference between your observed, which are the values actually obtained, versus the expected values. Okay, so let's move on to another example. So we're going to do the Roberts data set, and this study was looking at Kulebach, or Kulebach, I don't know how to pronounce it, dieback, versus this position in the floodplain, whether it was at the top, middle, or bottom of the floodplain. So we're going to run the CSV, and we'll check out what the data set looks like. All right, so again, here's the Kulebach. So it was measuring whether there was Kulebach dieback or if the area did not have any Kulebach dieback, and then the position in the floodplain, and then your count. And again, count is your response. So this is the long format of the data. Let's put it into the pivot table using the xtabs function. Okay, so now we can get a better view of the counts for each combination of the variables. And then looking at the output, so the reason why we get this little warning down here is because we have a 0 value here for top and width. So it's just yelling at us because of that, but it's no big deal. It's more of a warning than an actual error message. Okay, so here we get a p-value that is less than 0.05. So as a result, we can say that we can reject the null hypothesis, and that there is, or you can, the amount of Kulebach dieback is contingent upon its position in the floodplain. Okay, so let's look at the observed and expected values. So here are the observed, and again, we're getting this little warning because of that 0. Okay, and also I think one of them is, yeah, so one of them fails the, 2 of them fail the assumptions, but that's okay. Okay, so here we have our observed, and here we have our expected. Let me make this a little bigger so we can, here we go. Okay, so then we'll run the actual residual so we can see the actual deviance or the direction of deviance between your observed and your expected. Okay, so interpreting this, the amount of decay is greater than what is expected in the bottom of the floodplain and less in the top. Sorry, less in the top of the floodplain. So without dieback is greater than expected in the top because we have a positive number and less than what is expected in the bottom. And this 0 means there's no change between them. It's your observed value is the same as your expected, so there's no deviance there. All right, so let's actually calculate the odds. Now, calculating the odds can only be done between pairs or two variables, and we happen to have 3. So, well, we have 3 levels for position. So we have to manually calculate the odds for each combination. So the odds of having dead trees in 3 categories are as follows. You have the odds for your bottom level, you have the odds for the middle level, and then again, top cannot be calculated because they're both 0 values. And again, that's because your observed value was equivalent to your expected. So looking at your observed table, to calculate the odds of having dead trees in the bottom position of the floodplain, we would do 15 divided by 13. And that gives us an odds of 1.15. So the odds of having dead trees, the odds of having dead trees at the bottom of a floodplain versus not having any decay is 1.15. And then for the middle, you would calculate it using these values here. And again, you can't calculate top because you have 0. So for the middle, you would do 4 divided by 8, and you would get 0.5. So the odds of having tree decay in the middle position of the floodplain is 0.5. Alrighty. So those are the odds proportions, and then we're going to calculate the odds ratios. And again, the odds ratios are the proportion of diagonals. But since we have that 0 value in the top position, we have to add 0.5 to all of our values. Otherwise, R gets very angry with us, and then we can't run the odds ratio test. So we're gonna, I'm gonna run the observed chart just so we can have it close by. Okay, so again, we're gonna do our proportions. So to calculate the odds ratio for bottom versus middle positions, we would take 15, and again, we're adding 0.5 to everything. So 15.5 times its diagonal, 8.5, and then 4.5, and sorry, that's divided by 4.5 times its diagonal, 13.5. So you're kind of making this cross pattern. Think of it that way. All right, so we're going to run that. Okay, so the odds of having tree decay in the bottom of the floodplain versus the middle of the floodplain is 2.17. Now, the odds ratio for bottom versus top, we're going to do 15.5 times its diagonal. Now its diagonal with the top is 17.5. So we'll do 15.5 times 17.5 divided by 0.5 times its diagonal at the bottom, which is 13.5. So the odds of having tree decay or coolabud decay in the bottom of the floodplain versus the top is 40.19, which is huge. All right, so let's do the middle versus the top. So the odds ratio for this would be 4.5 times its diagonal, 17.5, divided by 0.5 times its diagonal, 8.5. So you run that, and then you can interpret it as the odds of having coolabud decay in the middle of the floodplain is versus the top is 18.5. Okay, so there's also this function called the odds ratio .wald, and this is in the EpiTools library. So you have to download that library, but this will do will basically do this for you against a reference level, and in this case we'll set the reference level as bottom, or the bottom position. So first, again, because we have that 0 in top position, we need to add 0.5 to everything. So we're going to build a temporary model. I'm going to call it a temp, and add 0.5 to our model. I can actually run this correctly. There we go. Okay, so now this is our new data. So we have 0.5 added to everything. Okay, so you're going to install this package called EpiTools. I already have it, so R is yelling at me. But if you don't have it, just go to Packages and type in EpiTools. And then we're going to run the library once you have it installed. Okay, so again, the function is called odds ratio.wald. So we're going to run it on our new model, which we've called temp, which has 0.5 added to all the variables. So we run that. Don't listen to the little warnings here. I'll explain those. Well, you can listen to them, but just because they're more of warnings rather than errors, so don't freak out. Okay, so again, this is giving you the odds of all the variables using against a reference level, and in this case the reference level is the bottom position. So you get your p-values under a Fisher's exact test and under the chi-square test. So the reason why you have NA for bottom is because bottom, again, is your reference level. And then, so the odds of middle versus bottom are given by these values, and then top versus here. Sorry, these are your actual odds, and then these are whether they're significant or not. So the odds of having, given this odds ratio, the odds of having plant decay in middle versus the bottom, I think it's this value here, and then top versus bottom would be somewhere in this range here. Okay, so you can also, and so the reason why this is yelling at us is because we get a really low value for Fisher's test, but again, that's more of a warning than anything. So we can also manually set the reference level. So here we can reverse the order of the rows so that we compare everything to the top rather than the bottom. So now these are odds ratios versus the top as the reference level. We can run that. Again, R is yelling at us, but that's okay. Okay, so we see our little count table. Here are the odds ratios at the 95% confidence interval. So these are like your confidence intervals, so you can tell if they're significant. And then the p-values given under the Fisher, exact test, and the chi-square. So you can interpret whether they're significant or not. And in this case, all of them are significant. Okay. So there are many ways to answer this question of the relationship between variables. And so you have contingency tables, and then there's another thing called log linear models. And they're another way of asking essentially the same question. So the nice thing about these log linear models is that they also allow you to compare more complex models, like models that contain more than two predictor variables. So we're going to run an example, but we're going to fit it with two variables. So you need your mass package for that. So run library mass if you already have it installed. We're going to create a model. We're going to use the log LM or log linear model function to create it. Count is our response, and then our two predictor variables, the position in the floodplain and Coolabah, whether it did or did not have dieback. So we're going to run that. Okay, so this gives us the output. And so you have your x squared value. Here's your likelihood ratio and the Pearson's x squared value. Your degrees of freedom, and then your p-value, which is what we're really interested in. So we're going to look at this right here. Okay, so we get a p-value that is significant. It is less, way less than 0.05. So we reject the null hypothesis because there is an association, and the variables are not independent. So that's how we use log linear. So let's try one where we have three predictors. So I actually have to reset my working directory for this because I have it saved somewhere else. I had a little reminder from myself. Okay, so we're going to run this ants data set. Now I personally, so I did this project in Ecuador during my the summer of my junior year of undergrad, where I was studying the mutualistic relationships between non-myrmecophytic cecropia trees and Azteca ants. Between cecropia trees and Azteca ants. And so I was looking at non-myrmecophytic species, which are those plant species that do not use ant defense mechanisms. And so I was looking at the relationship of what kind of defense mechanism they were using and seeing if that was why they were not being predated on by leafcutter ants. So I was doing these chemical extractions and all this fun stuff, but I was finding ants in my backpack for a good 3 months after the trip, and I hated ants afterwards. So when I saw this, and they do a lot of, in this experiment, they kill a lot of ants. So I was like, yay, kill all the ants, but it's actually very sad. So this experiment purposely cut the life expectancies of certain ants or removed their kind of defense systems. So the life expectancy of foragers were shortened by poisoning with carbon dioxide. So they were testing the question of whether these shorter-lived ants would travel more to forage under high heat conditions. So there were three predictor variables that we're interested in evaluating. And as a result, we have to conduct or construct what is called a three-way frequency table. So we're going to use the xtops function again to make our pivot table. And again, here's our three predictors. So we have group type, activity, and temperature versus the response variable, which is our count. And we're going to use the ftable function to print it out. All right, so here's our pivot table. which is nice and easy to read. So here is these are your group types, and then temperatures and activity. So there were two group types. You had your controls and your experimental. Activities, you had foraging or nesting, and then for temperatures, high or optimal. So I was looking at the different combinations of those, and here are your counts for those combinations. All right, so let's run summary. So we're going to do the chi-square test of independence. All right, so here we see a p-value that is greater than 0.05. So as a result, before I jump, the null at this point is that there is no significant difference between observed and expected value, whereas the alternative hypothesis is that there is a significant difference between observed and expected values. So because we have a p-value that is greater than 0.05, we fail to reject the null hypothesis, which is, in this case, good, because we don't want to have a significant difference between the observed and expected values. All right, so now we have to create manual log linear models because we have these three predictors. So we're going to build 4 models using the GLM function. And the first model that I'm going to create is what I'm going to call mod R in reference to our original or reference model. So this tests count, but we're calling count frequency instead. And it's like a normal model. We have temperature, activity, group type, our normal predictors. So we're going to run that, and that builds model R. Now the second model, or mod 1, that I'm building, if you notice, has an interaction term placed between temperature and activity. So I placed it here because I want to test to see if there is an interaction between temperature and activity. So right now I'm testing, by doing that, I'm going to test for a two-way interaction. So I'm going to run that model. Model 2 is essentially the same thing, except I place the interaction term here between the combined temperature and activity to see, and between that and group type. So I'm seeing if there's an interaction between temperature and activity combined and group type. So we can run that model. These are all being stored right now. And then the third model, the fourth model I'm running, which is mod 3, tests for a three-way interaction. So you have an interaction term between all three predictors. So we'll run that. Again, that's a three-way interaction. Okay, so the first thing we're going to do is an ANOVA test. And we're going to use the actual ANOVA function for this to get the ANOVA output. So we're going to test the reference model versus model 1. And this is a test of joint independence. So what we're doing is by testing the mod 1 against the reference model, we're testing to see if the addition of the interaction term causes a significant difference from the original model. And therefore that would say that there is a possible two-way interaction that's occurring. And we'll do this for each model, comparing each new model separately against the original model, which is our reference, to see if the addition of that interaction term causes a significant difference. So again, for this, I'm testing mod 1 versus mod R, which is our reference. So if I run this and there is an interaction term, if I run this and the significance does occur, then that would mean that there is an interaction between temperature and activity that is significant or is present. So let's run that and see what happens. All right, so the p-value I get is significant. So since it's less than 0.5, I can say that there is an interaction or an association between temperature and activity. All right, so now we're going to test model 2 versus mod 2 versus the reference model. And this is for conditional independence. So again, this one was testing temperature and activity combined to see if it interacted with group type. So let's test that. All right, so the p-value we get for this is greater than 0.5. So as a result, there is no interaction or association between combined temperature and activity versus group type. So let's run the last one, which is mod 3 versus your reference model. So remember, mod 3 was the one that had an interaction term between all of the predictors, and therefore, because of that, was testing for a three-way interaction. So we'll run that, and we get a p-value that is greater than 0.5. So there is no interaction or association between all three predictors. Now, because we have three predictors and there is no three-way interaction between them, as we've justified from this value here, we can perform what is called a Cochrane-Mantel-Haenszel test. Now, this is a chi-squared test of the null that two nominal, or your named-only variables, are conditionally independent in each stratum, assuming that there is no three-way interaction. So in other words, it tests that the independence of two nominal variables that are stratified by a third nominal variable when there's no three-way interaction present. So you have no three-way interaction present, but there's a possible two-way interaction. So you essentially have what is called a 2 by 2 by k interaction table. Let me scroll down here. Okay, so you have a 2 by 2 by k interaction table, and this is a case of interest to researchers in many areas, and that usually occurs when there is no three-way interaction present in the 2 by 2 by k layout. So in this case, a question of common interest is whether there is any relationship between the two main variables of interest after controlling for that stratification variable. So the common way to assess relationships in a 2 by 2 way table is through the odds ratio. And the most popular estimator of the common odds ratio across the k strata was actually suggested by Mantel and Haenszel, who also provided a chi-squared test of the null hypothesis that the common odds ratio is equal to 1. So if we reject the null under a Mantel-Haenszel test, then there is a significant association between variable 1 and variable 2 within each stratification level. So for example, say you wanted to compare success and treatment groups, but the treatment groups were administered at 3 different times of day. You say you had morning, afternoon, and night, and that you wanted your test to actually control for this. Using the Mantel-Haenszel test, you could then operate on a 2 by 2 by 3 contingency table, where the third variable is the one that you're controlling for. And in this example, it would be time of day. So you're testing the interaction between your success and your treatment stratified for time of day or controlled for time of day. So implementing this in terms of the study that we're looking at with these little ants, we can use the Cochrane-Mantel-Haenszel test or the Mantel-Haenszel test to test for two-way independence, assuming that no three-way interaction has occurred. And again, we found that this is true by running a model with the interaction terms between all three variables. So since the p-value was not significant for this model, there was no three-way interaction. However, again, there may be a two-way interaction occurring somewhere. So we will use the Mantel-Haenszel test to determine the presence of a two-way interaction or two-way independence in the absence of a three-way interaction. So the data is entered as a data frame for your counts, and we're going to use the xtabs function to make a contingency table. So when you set this up, we're going to have the two variables that we're interested, or 2 predictors that we're interested in looking at. And then your last variable that is put in is the one that you're controlling for. So in this case, we're going to end up testing to see if there's an interaction between temperature and activity controlled for or stratified by group type. In this case, the 2 group types were controlled and experimental. So we're going to run that. Okay, so this is for, so here we have the control group, and we have the counts for the control groups. And then we have the experimental groups, and we get the counts for the experimental groups separated. So then we can run a flat contingency. So this is the 3D contingency table. Again, controlling for group type. So now we can make a flat contingency table using the ftable function. Okay, so here's the control group, and here's the experimental group, and then the counts according to different pairings of the variables. So let's run the Mantel-Hines test. So that's the Mantel and then HAEN.test function. And we're going to continue using xtabs within that. Remember, the last value you put in is the value that's being stratified, or the value that you're controlling for. So we're going to run that. Okay, so interpreting this output, we see that, okay, so we get here's our p-value. So there is a relationship between temperature and activity controlling for group type, because the p-value is approximately 0.013, meaning that it's less than 0.05. So since we have a significant p-value, we reject the null hypothesis and accept, or in favor of the alternative hypothesis, that the value of the common odds ratio is different from 1. And then you can also validate that by the confidence interval. So the confidence interval does not include 1, meaning it's significant. So a different way of approaching it would be to perform a Fisher's exact test. Now, Fisher's exact test is a statistical test that is used to determine if there are non-random associations between 2 categorical variables. So you can't use it for 3, you can only use it for 2. We're going to use the Fisher.test function. And notice where you can, since again this can only be performed on 2 variables, we're taking out group type and we're just looking at temperature and activity. So this will produce the outputs on a collapsed 2 by 2 table. So we're no longer in the realm of 2 by 2 by k, we're in 2 by 2. Okay. So if you look at, so here's our p-value. We have a significant p-value, and our confidence interval does not contain 1. So both of those say right there that we reject the null hypothesis, meaning that there is significance and there's a likelihood that the common odds ratio is different from 1. So we can also use a mosaic plot. So we'll create the xtabs. Sorry, we'll create a new model using the xtabs and then create a mosaic plot of it. We'll zoom out. Come here. Okay, so here we have our 2 values of temperature. Here's this column represents optimal temperature, and this represents high temperature. And then these 2 boxes at the top represent the values for foraging activity, and then these represent nesting activity. So again, you interpret it using this color gradient here. So the mosaic model shows that there is an interaction because we have this zigzag pattern between the spaces, and because they're not in proportion. So here, at optimal temperatures, the ants were more likely to, or these short-lived ants were more likely to nest than forage. And that observed value is less than what is expected, and that's because it's in this area here. Under high temperatures, again, these ants are more likely to nest than forage because of the size difference in the boxes. And the actual value of that observed value is greater than what is expected, and that's because the box falls in this area here. Okay, so in conclusion, what we can really draw from this, so we had an odds ratio, I think like 3.5 divided by 9.5, and that gave us an odds ratio of 0.368 for the odds of short-lived ants foraging during high temperatures. And the odds of a control ant foraging at high temperature was, I think, 0.29. Let's bring up our results. If I can find them. Oh, yeah, there. Okay, so yeah, so the odds of a control foraging at high temperature was 0.29. Again, you do that by dividing the one that you're interested in by its opposite. So the odds ratio then, doing that proportion of the diagonals, would be 1.2517. So short-lived ants are about 1.25 times more likely to exhibit risky behavior. In other words, foraging at higher temperatures. And so therefore, a worker's strategy of foraging under risky circumstances appears to be fine-tuned to its life expectancy, which makes absolute sense. Life history theory predicts that eusocial insects with short life expectancies will undertake these risky foraging behaviors because their chances of food acquisition in the future are small. So they'll subject themselves to higher risk because of higher mortality in order to secure the survival of the healthy ants. So in order to survive, ensure the survival of the colony as a whole. And that's it for contingency tables.